so I'm going to get started. So before the quiz, which is going to be at about 9:15, I'm going to talk about how records or structures work in C and C++, and how pointers are related to that topic. Okay. So the first thing we want to do is to take a look at something that we did last time. Okay, so let's see. I think we still have it right there. Okay, so what we worked on last time is an example of how to use a structure. So we'll take a look at the definition of a structure first in C and C++, which is nothing new. I mean, this is something that you should be at least somewhat familiar with. Okay, maybe not, you haven't used it a lot, but this is something that should not be new entirely to you. So we have a structure, which is basically the same thing as a class. For those of you who are familiar with what a class is in C and C++, and also in Java. So in this case, we have three members. CH, I, and buffer are members of the same structure. The one thing you can count on is all members of the same structure are kind of bundled. Okay, now there may be some gaps and spaces in between the members, but they're all at the same place. In other words, the compiler will never scatter the members of one particular structure, so it's interleaving with members of another structure. That would never happen. Okay, so you have one chunk of memory allocated to one single structure, and it's just a matter of where each member is within that chunk of memory. That is the question. Is that okay so far? Okay. So last time, we took a look at this particular program, and I think we ran it too. We actually made an executable out of it. So main is already made. So we'll go ahead and do a gdb main, and main doesn't. Is main actually? Oh, it's called struct. Okay, so the main program doesn't really do much. Source file is more recent than executable. Alright, so we might need to fix something in here. Nothing to be done for main. Alright, there we go. Fatal error, no such file. There we go. It compiled everything, but it did not give me an executable. Struct is an executable, but this time it did not. Alright, so main is an executable. It depends on the source files and the assembly file. We have one assembly file here. And let's get rid of this and put it back in here. Nothing to be done. Forgot that I changed the name already to have an EAK extension. That's why it won't compile using make. Still won't do it. Okay, we'll do everything by hand first, because the point is to show you how memory is laid out within the structure. So right now we have, okay, let me hide the other screen a little bit because it's kind of distracting. I'll make this one bigger. There we go. Alright, so the purpose of this program is to show you what a structure looks like, particularly the locations of the different members. We'll put a breakpoint on line 6. We're not really going to run the program. That's not really the point of this particular program. So what we want to do is to print the entire var1 Now var1 is declared using struct x, which means it is a structure. So if you print var1 as a structure, it will print out all the members of that structure. In this case, var1 has a few members. The first member is a ch, or a character, which has 125, which is the ASCII code of the closed curly brace. That's why it looks kind of funny, because this is actually not the closed curly brace for the open here. This one is actually in quotes, which means it is just the character corresponding to ASCII code 125. I as a member is an integer, and this so happens to be the random bits in at that place when we look at var1, because var1 at this point is not initialized. Buffer, on the other hand, is an array of some numbers of characters, and it has all of these individual bytes in it at this point. So that's how we show the individual members. But what I'm really interested in is not really the content, because it is not initialized. What I'm interested in is the address. So var1 is located at this address here, but what about the members of var1? var1.ch, which is the member ch, is at exactly the same place. You can see that the first member of var1 is ending with, the address is ending with 4c, and the address of the entire structure is also ending with 4c. Now that is not really surprising, because we don't want to waste any space at the beginning of a structure, so we put the first member of a structure to the very beginning of the entire structure. But when you look at the other members, like I is 4 bytes away, which kind of makes sense. Well, in a way, because I is a 32-bit integer, and we don't want I to be following ch immediately, even though ch as a char only needs 1 byte, because we want everything to line up by 4-byte boundaries. Does everybody understand why it is advantageous or more efficient to have all the constructs aligned at 4-byte boundaries? It's a 32-bit architecture, okay, which means with each memory bus operation, we can grab 4 bytes at a time. Is that part okay? So the width is 4 bytes at a time. It's kind of like you can go to the library to get me a few pages out of a book, photocopies of 4 pages in a book. And it is 4-page aligned. Okay, so the way you access things from the library is you can only access page 1 to 4, 5 to 8, 9 to 12, and so on. Okay, so if I try to get pages, let's say from page 6, 7, 8, and 9, you need 2 trips to the library. Is that making any sense? Because the way you access a book in the library is it has to be 4-byte aligned, or 4-page aligned in this case. So if I want to get something across the 4-page boundary, then you have to make 2 trips instead of 1, even though in theory you're only still getting 4 bytes. I'm only interested in 4 bytes, but 2 bytes belong on one. You need 1 trip to get the 2 bytes, and then you need another trip to get the other 2 bytes. And that's why the compiler by default will try to align things so that the things that require 4 bytes to begin with, like I in this case, is going to be at a 4-byte boundary instead of immediately following ch, which would not be a 4-byte boundary. Yep.
So then we're talking 8 bytes on the 64?
That is correct.
Okay.
Yep. So as architectures evolve and the width of the data bus get wider, it will try to do the alignment like that too. It's a waste, okay? It's definitely a waste, because now you can waste up to 7 bytes just to get the alignment to like 8-byte aligned. But since we have 16 gigs of RAM these days, as opposed to good old days, most people only have 2 gigs, so it's not as big of an issue. All right, so we'll single step into the subroutine. Okay, this is in subroutine initx. And now we're trying to access member I of where the pointer points to. So in this case, PTR as a pointer is a pointer to a struct X, and we are using it to access element I. So the way this works is PTR is pointing to the beginning of the entire structure, but since we want to access member I of the structure pointed to by PTR, we are basically adding the displacement from the beginning of the entire structure to member I to the address already stored in PTR in order to access member I. In other words, if I look at the address of PTR points to I, And if you want me to be more specific, this is the address that I want to look at, is the address of member I of the structure pointed to by PTR. It is still 4 bytes away from the beginning of the entire structure. So are we doing okay so far in terms of accessing individual members of a structure when the structure is pointed to by a pointer? Is that okay so far? Okay. And that's going to be, the focus of what we'll be talking about today. There's a new homework assignment that has to do with structures. The code is already written in C, so once again, your job is to translate C code into assembly code. The C code is already written. You can test it. You can actually go through GDB to find out how it works. And your job is to translate that into assembly code. But it does involve the use of structures and also pointers. So in a certain way, you can call that like a data structure type of exercise. But since you're not going to come up with the algorithm or the original C code, it's not the same complexity as what you will have to deal with in CISP 430 or even 400. Okay. So are there any questions related to structures, pointers, and those related concepts? No questions? All right. And we are still waiting a little bit for the quiz question to release. Let's take a look at the homework assignment. Start my browser. And by the way, the regulation has changed. They are now not requiring a platform to be authorized before it can be used in classes.
For now.
Yes, for now. I do not know who convinced the district to change their mind, but I'm pretty sure it was not me. Yep.
I was wondering, question 3 for the exam isn't up yet.
It should be up already. I graded that already. I can show you where it is. Maybe it cannot. Okay, I've hidden it, but it's already scored. So when you look at the grade sheet, it is now actually reflecting the score of that
the
part
total, the little thing right underneath the other two.
Yeah. Let me turn it on so that it's not hidden. I forgot to turn it back on, after grading it. Or at least I thought I graded.
Sorry.
I think I graded it. It's just that I did not unhide it. So let me unhide it first. Now it's shown. So it should be visible now. I also adjusted the gradebook, so it is now actually reflective of all the work that has been graded at this point. So that is actually a more accurate reflection of your grade at this point. Before the final, which is 40%, is actually a part of it, and that's why the entire class is having D's, because that's 40% right there. And then the quizzes were not factored in, and now those are all factored in, and I think people will be looking at a much more realistic picture of what your current standing is in this class.
I preferred my previous grade of 1,000%.
1,000%.
That was
Yeah.
pretty nice.
But the question is it reflecting your grade correctly?
No, it wasn't at all.
Okay, so what we are going to do is, this is your new homework assignment, and it is still hidden. Oh, no, I clicked the wrong link. I clicked duplicate instead of show.
Now we have 2 seconds.
Now we have 2, yes. Okay, let's get rid of the second one and show the first one. There we go. Okay, so this is an assignment. It's called arbitrarily long strings. Okay, so basically when you declare a string in C, not in C++, okay, because there is a string type in C++ that can deal with any arbitrary length of text. But a regular string in C is non-terminated. And you can only allocate so many bytes each time because you don't know. If you don't know how much text needs to be stored, then how are you going to do the allocation? Are you going to allocate 256 bytes, 1 kilobytes, 4 kilobytes, 10 kilobytes, 16 kilobytes? Well, you don't want to allocate way more than what you need, but since you don't know how much you need, you cannot actually do the allocation either. So the way this works, with this homework assignment, which is called arbitrarily long string, is it will break a string into little chunks, okay? And one chunk can be 4 bytes, 8 bytes, doesn't matter what it is. And when you run out of a chunk, it will allocate another node and have the first node to point to the second node. And when you run out of bytes in the second node, it will allocate the third node, where the second node will point to the third node. So it basically forms a little chain of these structures, having one pointing to the next one. So this way, by adding more and more nodes, I can extend the length of a string, and I can make it arbitrarily long as I can still allocate these nodes.
So
Yep.
the nodes form a linked list?
Yes, it basically forms a linked list. But as I said, the code is already written in C. It's tested, it's written, and your job is to translate that into assembly. Okay. It is now 9:16, so the quiz question should be open. So let's go ahead and answer the question. And I'm hoping that you guys paid attention, at the very beginning part of this lecture, because the quiz question has to do with exactly that. So I was originally intending to use a file, that's why you see all the pound signs. So basically, I'll just describe it a little bit while you guys get your paper and pencil ready. So assume that x_a as a symbol is the displacement in number of bytes from the beginning of a struct x to member A of a struct x. Okay, so x is the name of a structure, and A is the name of a member of a struct x. You can assume EAX is a pointer to a struct x. In other words, the content of EAX is the address of a struct x construct somewhere in memory. Okay, it points to it. You can assume a member of struct x, member A, excuse me, you can assume member A of struct x is a 32-bit integer. So all I want is for you to write the code in assembly instructions to initialize member A of the struct x pointed to by EAX to 0. I just want to reset that to 0. And the hint is if you use cisp addressing modes that we have been using for a while now, you only need one instruction to do it. So you kind of have to think about the addressing modes that we have been talking about for a while already at this point, and then think about what instruction would do this. So to give you a more complete picture, we have, somewhere in memory, we have a chunk of memory called struct x. Okay, it is following the structure of an x. We have EAX as a pointer pointing to the beginning of the structure, and then member A is somewhere here. Okay, let's say that's member A, and the number of bytes starting from the beginning of the structure to the beginning of member A is known as x_a. And the question now is, how do I zero this content here to 0? So I want to change all of that to 0. And it's a 4-byte thing. 32-bit. Question? No? Okay. It's open book, open notes. If you want to refer to stuff that we have talked about in the previous class, that's fine too. And hopefully that's not just a timestamp and what I talk about in this class.
I have a lot of those.
Well, it's helpful. I mean, it's helpful for studying. I'll give you guys about maybe 2 more minutes, and I'll give you a little bit more hint for those of you who can use a little bit more hint. We know the instruction has to involve EAX 0 and X underscore A. That much we know for sure, right? And we also know the instruction has to alter or change the content at this location. We also know the instruction has to do with a 32-bit thing. So all of those are hints to help you narrow down to which instruction, and then you have to choose the addressing mode. There are only a few addressing modes that are actually relevant in this case. If you cannot do it with one single instruction, I will still take the answer if you use multiple instructions. I mean, that's using the RISC way of doing things. Does anyone need more time? It's all good? You need more time? Okay. Are we good? Okay. All right, so let's go ahead and collect all the questions. Make sure your name is on it before you pass it along. I hope no one is intentionally writing the wrong answer and then put the name of somebody else on it. Especially someone who's not currently in the class. I think there are at least 2 people who are not currently in the class.
I think that's what people are doing to me.
That would explain my grade.
Exactly.
All right. So the answer to this question is something that we'll see a lot today, and we have seen it already. Okay. The answer is I can just do it here. The answer is a move long instruction, because the move instruction is also known as the copy instruction. This is the one thing that we need to use to change or alter the content of a memory location. The 0 goes into the first operand, but it has to be an immediate operand, because if without the $sign, it is a direct operand, which means we are not copying from location 0. With the $sign, the 0 becomes the actual value that we are copying to the destination. So that part is important. And then the most quote-unquote tricky part is x_a is telling us the displacement, or we are off by this many bytes. And the register EAX becomes our base register, because it tells us where to go. So when you combine x_a and an EAX, this particular addressing mode is called the base addressing mode, or the base operand. And what it does is it adds x_a to the value of EAX, and the sum becomes the effective address. That is where we are going to store the first operand. So that is the answer. And I will try my best to give you guys partial credit, because there are multiple components to this instruction, but the second operand is the most important part. Okay? Have we seen this type of operand in the previous class, in the one before that? And how do we use this particular type of operand for?
For accessing different parts of the stack.
Yep. And instead of using EAX inside the parentheses, which registers? Well, there were two, because we originally used one particular register, and then we switched to another register later on. So which registers did we use inside the parentheses before? Originally ESP, because we said, okay, the stack point is pointing here, and we want to go here. And then later on we said, okay, I'm done counting the number of pushes and pops, so we switched to the frame pointer, which is EEP. So it's the same addressing mode, just applied to access, in this case, a member of a structure pointed to by EAX. Yep.
Say there was another member above A to construct. Would you add 4 to it, or?
I typically would use a different symbol, for each member. So each member would have its own symbol.
Oh, okay.
Yeah. So this way, and these symbols will be redefined by a C file that depends on the actual .h file that has the structure definition. So this way, my assembly code can get updated as quickly as someone can update the header file in C. And that's something that we were just getting into in the previous class. All right. So let's go ahead and take a look at the homework assignment, because this is actually closely related to the homework assignment that we'll be doing for the next week. It's probably going to be our last, homework assignment, unless someone wants to do something, and make it due on the week of final. Pick me, yeah. All right, so it's called longstring.tar.gz. That's the name of the file that you will be downloading. And let's take a look at the code that is involved. And I'll show you a few steps, of how to get started with the homework assignment, because I think that might be helpful. So let's go ahead and go to downloads, extract the tar file. And when you get to the subdirectory, it already has the necessary files. The make file is already pre-made, so if you say make clean, and then make again, it will, unused. Okay, so it's just warning that your PTR is unused in str write, okay, because it's an extra local variable that I forgot to delete when I copy it. Okay, so let's take a look at what the program does first. Okay, so here's main, and it's waiting for something from standard in. In other words, it reads as many bytes as you want to specify from standard in, and then it will store the input into a long string, and it will print the long string twice. Okay, so whatever you specify in the standard input, I'm going to type something that may not be very long, okay, and then you press the Control-D key on your keyboard to mean end of file, and it will just echo it back twice. But it will do this regardless of the length of the input file. So if I give it something that's a little bit longer, let's just say it is strread.c, which is a text file, the output would be the same file, but twice. So it will just repeat outputting it twice. Okay. And when you look at the code of main.c, it's really simple. All it's going to do is to pound include lstr.h, which is a header file that includes the definition of the structure as well as the prototypes of the two subroutines that are being used here. The first one is on line 7, which is lstr read. It's reading from file descriptor 0. That's what the 0 is for. And we are reading into a pointer of a struct lstr node, long string node, and you're passing the address of a pointer in this case. So we're not passing the pointer itself, we're passing the address of a pointer because the subroutine is going to change the pointer itself. The pointer does not need to be initialized. It will be initialized in the subroutine itself. The two other calls on line 8 and line 9 are basically just saying, okay, now that we have a long string stored in the LST long string node that long string points to, let's print it out. And we're just printing out twice. So are there any questions about main.c? There's nothing you have to do with main.c. You can just leave it the way it is. There's nothing to change here. Yep, go ahead.
Just curious, why twice?
Just so that people do not use a different approach to do the same thing by echoing the characters one by one.
Okay, gotcha.
So this way it has to be stored somewhere, and because you don't know ahead of time how big of a file I'm going to give you, so it doesn't really help when people just kind of assume and say, oh, I'm going to assume it's going to be 4 kilobytes or 8 kilobytes. Nope. I can give you something that's really, really big. All right. So we will now take a look at lstr. But let's look at the header file first. The header file is nothing really too suspicious. It just pound includes lstr def, which has one single pound defined definition because I want to separate it from this file so that you can use it in the assembly language file as well. The structure of an lstr node is fairly simple. Okay, it has two members only. The first member, which is on line 8, is called a chunk. A chunk is basically just an array of characters. But the length of a chunk is determined by lstr underscore chunk underscore size, which is a macro definition contained in lstrdef.h. So that's why I kind of separate it into two, because you will need lstr chunk size in your assembly code as well. You don't want to make the assumption it's 4 or 8 because I can make that change, and I want your code to I want make to be able to update everything, including the update of a chunk size. Now, what is interesting, and some of you may not have seen something like this before, is I have a p next as a member. Okay, that's just the name of the member. I use a little p as a prefix because it is a pointer. Okay, it's a pointer to the next node, and that means it is pointing to another list long string node. So this is the type of p next. It is a pointer to a struct lstr node, and this is inside the definition of a struct lstr node itself. There's no problem because on line 9 I am not using a structure. I'm only referring to the pointer to the structure, and the pointer to anything is only 4 bytes, regardless of what it is pointing to. Is that okay? So as far as the compiler is concerned, it doesn't really need to know the details of a structure if I just need to declare a pointer to the structure. Is that okay so far? So that's why line 9 is not a problem. It's not quote unquote recursive in any way because I don't need to know the detail of the structure in order to declare a pointer to the structure itself. Are there any questions at this point about this file, lstr.h? This is not something that you can pound include into your assembly code because the assembler cannot handle the definition of a structure. So this is not something that you want to pound include into your assembly code file. Yep, go ahead.
Why do you have a double pointer on line 12?
Because it has to be a double pointer, because we are not, because the subroutine lstr read has to change a pointer. So the only way to change a pointer is to pass the address of a pointer, and that's why it looks like a pointer to a pointer, because it really is the address of a pointer. Yep.
Is that way there's a constant on line 13? You don't have to
change?
On line 13, it's a const, just so that the compiler can make sure that I'm not changing the nodes. Because when I'm printing, a long string, I just need to read the content of a node. So I just want to make sure that the compiler will do some extra checking just to make sure that I'm not accidentally overwriting anything in the nodes. That's a typical thing that people should do. Whenever you write a subroutine that is not supposed to change the parameters or particularly what they point to, you should use a const just so that the compiler can check, double check for you and make sure that you're not changing anything. All right. Any other questions about lstr.h? Okay. So this is lstr.h. Your job is to translate lstr read and lstr write into assembly code. You don't have to do both at the same time. Do one at a time, okay? To make your job easier, only do one at a time. This is the easier one to change. So basically what happens is one lstr node will look like this. The first part is going to be a chunk of characters, okay? And I can change lstr chunk size so that it goes from 4 characters to 8 to 16 or back to 2. Okay, so that's up to me to decide, and I can change it. Your assembly code has to be able to deal with that, okay? Because you have to make the assumption that I can change the definition of lstr chunk size, type make, and then your code will get updated correctly to reflect the actual chunk size. But the trick is the second member is a pointer. So it points to another thing that looks exactly like this. And this potentially points to another thing like this. The last item is going to have this as a null pointer to indicate that's the end of the entire chain. And whatever you pass, which is called the parameter head here. So head is the head pointer. It points to the very first node. Are we doing okay so far? And the way it works is it will go through each chunk and it will print each character in the chunk sequentially. And it will, at the end of the first one, if it is not a null character, it goes to the next one, keeps doing the same thing. Then we go to the last one, and it will be null terminated. In other words, when you combine all the chunks of all the different nodes, it is still a null terminated string. So when I get to a null character, I'm going to stop. So when you look at line 11, the condition to stay in the loop is when I'm still pointing to a node. In other words, if I get to the null pointer here, and there are no additional nodes, I have to stop. Okay, that's the first reason to stop is I'm not pointing to a node anymore. And the second one is if I am pointing to a node and the character that I'm going to print is non-null, then I still have to keep going, which is okay, here's the character that I have to print. On the other hand, if the character that I'm about to print is a null character, that means I have hit the end of a null terminated string, and now I can stop, get out of the loop, and that's the end of this particular subroutine. So that's how it works. In the loop, it looks a little bit, complicated, but it's not something that we have not encountered. The write operation here is just relying on system surface number 4, which we have done already. Except in this case, I'm not just hard coding the file descriptor, because we typically hard code it to 1, file descriptor 1, but in this case I use fd as a parameter that is for lstr write, and I'm just passing it along, okay? But it will still have to go into EEX. The address of the element of an array pointed to by a pointer of a structure is the tricky part. Okay, so how do we get the address of an element of an array, which by itself is a member of a structure that is pointed to by a pointer?
Lots of offsets.
Huh?
Lots of offsets.
Lots of offsets, and you have to figure out how to combine the offsets. You might need to use multiple registers or just use one, but you have to do the calculation. Okay. The nice thing is this is an array of characters, so there's no scaling involved. Okay, if I change by 1, then the address is also changed by 1. The last one here means we're outputting 1 character at a time, so we're processing 1 character at a time. Pretty much consistent with usually what we do. The next line is basically saying, okay, if we have just printed the last character of one chunk, which is this guy here, then it's time to move on to the next chunk. So that's why head gets head points to next, which is basically saying, okay, take this pointer, and now head points to this guy here. So we're just moving along on the chain to get to the next character print. I gets reset to 0 because now we're starting with a new chunk. We have to reset the index within the chunk to start from the beginning of that chunk. If we are not at the end of one particular chunk, then it's easy to get to the next character because we're still in the middle of a chunk. We just add 1 to I to get to the next element of the same chunk. Are we doing okay so far with the overall code of LSTR write? Or long string write? Okay. So if this is long string write, which is the easier one to implement, so if you want to pick one to implement first, I would pick this one first. But you can choose to do it, in whichever way you feel is better. This is LSTR read, which is a little bit longer, okay, because the reading process is a little bit slightly more complicated. So I'll just go ahead and explain, how it works, because once you understand how it works, I think it will help, with the implementation. We start on line 11, which is basically saying, okay, we start at the very beginning of a chunk. Okay, that's all that we are saying when we reset I to 0. Line 12 is kind of tricky because it has 2 assignment operations combined into one single line, because you can see there are 2 equal signs. The malloc is not an issue. Okay, even though we haven't really talked about how to do malloc from the heap, you just call malloc. Okay, let the linker deal with it. The linker knows how to resolve the reference to malloc, and the most important part from your perspective is to find out what is the size of a structure LSTR node. Okay, so we'll talk about that today. Okay, we'll talk about a technique to do that. So you need to push the size of one struct LSTR node on the stack. Call malloc just like any other subroutine. When it comes back, EAX, just like any other subroutine, has the address. So malloc is no different from any other subroutine that returns a scalar. EAX is the return value, which in this case is a pointer. So once you have the pointer, you want to store into whatever head points to, because we are going to change a pointer, okay, which is a parameter. But in addition to that, you also want to store into a local variable PER, which is not used in LSTR write, but it is used in LSTR read, and that's why we pilot complaints about the other one. So now we have to initialize and say, okay, let's make it a no string first, because we don't know what kind of a file we're going to read in. Okay, maybe it's an empty file. Okay, so we got to make sure that we don't, accidentally, end up with a string that has random content. We also initialize p next to null. In other words, if you are just allocating one node, we automatically say that, okay, this may be the last one. So until I have good reason to believe that we need another node, I will put a 0 into p next, so that we are ending that chain as it is now. We'll add additional node when we need to. Line 17 inside the do while loop is going to need a single character from FD, which is a parameter passed in, as a parameter to LSTR read. We're just reading one single character, and once again, you need to figure out how to specify the address of an element of an array, and that array is a member of a structure, and that structure is pointed to I in pointer. So same kind of arithmetic operation. Once you figure out one, you'll figure out the other. We're reading one single character at a time, so we're processing one character at a time from whatever input file we specify. And main only specifies standard in as the input file, so redirection will work well for debugging this program. Line 18 says, if we did not read a single character, which means something is wrong, we are hitting the end of file or something like that, then we're going to just say, okay, let's stop here. And to stop means that we put a null character into index I of chunk to basically say, okay, this is the end of the string. This is our null terminator. And that's it. The loop will exit afterwards, because when you look at the exit condition of the loop, it will take care of this. And then we also want to check, this condition here. Let me scroll down so that you can see the rest of the second conditional statement. So the second conditional statement is saying, if we did read exactly one character, but we are at the end of one chunk, okay, because the LSTR chunk size -1 is the index of the last element of a chunk. If we're at the end of one chunk, then it's time to allocate another chunk. So when we allocate another chunk, we overwrite the p-next pointer of the current chunk to point to the next chunk. And malloc is the same way as the first one. Okay, you just have to push the size of a structure onto the stack, call malloc. When malloc returns EAX has the pointer, has the actual address. We have to reinitialize I to 0 because now we are starting with a new chunk. We have to start from the beginning of the new chunk. P next, okay, PTR points to P next points to P next is null because now we are setting the next pointer of the node next to the current node to be a null. We are basically terminating that one first to make sure that we don't have any dangling pointers. And then after that, we can now move on and say that, okay, the current node is of no interest to me anymore because it is filled up. So now it's for me to move on to the next one that I have just allocated. So I will do the whole thing with the next node from here on. Else is corresponding to what if we did not read anything, or what if we're not at the end of, okay, this else actually should correspond to what if we did read something, but we are not at the end of one chunk. But this still works, okay? This still works because the exit condition will still catch and save, and it will get out at the right time, which is basically saying, if I did not read exactly one character from the read operation, it's time to get out. And that's LSTR read. So you have to convert both of these into assembly code. And there will be some chore, okay, involved. I would say this is one part that is a little bit challenging, okay? But since your chunk is an array of characters, it makes it a little bit easier because there's no scaling involved when you need to get the displacement from the beginning of chunk to the element that you want to access. All right. The other part that may involve a little bit more work will be this one here. But if you know how to get to the P next of where PTR points to, getting to the next one is just repeating the same process one more time. All right. Are there any questions at this point? Yep.
If we wanted to put a null in something, is that in assembly? Is that just 0?
Just a 0. Yep.
Just 0. Okay.
But the size of the 0 matters. Okay, so it depends on whether it's a null pointer. If it's a null pointer, you want a 32-bit 0. If it's a null character, you want an 8-bit 0.
Okay.
So you have to watch out for move L versus move B, because if you use a move L when you're supposed to use move B, you can be changing 3 additional bytes unintentionally, and those 3 additional bytes can be useful. On the other hand, if you're supposed to use move L and you're using move B, then you end up with 3 bytes that may not be initialized. They may have some garbage in it, but it needs to be initialized, but it's not. So you have to observe the width of the operations carefully when you initialize with 0, because when you use move something $0 and then use a memory operand, nothing in the operands can suggest the actual width. Because a memory operand can be 8, 16, or 32-bit wide, and the immediate operand can also be 8, 16, or 32-bit wide. So then you have to rely on the suffix of the instruction, the opcode, to really make it clear, are we moving byte, word, or long? Okay, thank you. You're welcome. So that's your, yep, go ahead.
Do you want us to adhere to standards like using the accumulating register for I?
No, the only standard you have to observe, since we don't have any actual return value, would be things that you have to conform anyway. Like when you call malloc, you have to push the parameter on the stack, because that's the way C subroutines work. When malloc returns, the return value is going to be EAX. So you better not have anything in EAX that you need to save for later when you call malloc, because it will overwrite EAX. malloc can potentially overwrite all registers except for the few ones that we know for sure has to be preserved. We know that ESP has to be preserved, the stack has to be balanced, EBP has to be preserved by the callee, and interestingly, EBX also needs to be preserved. So if your subroutine is going to use EBX, you need to save and restore that to make sure that the caller of your subroutine would not experience EBX changing. Is that okay? But all of the other registers, EAX, ECX, and EDX, those are free for you to use. You don't have to save and restore those. Yep.
So not to get too specific here, but by call malloc, you mean the assembly version of call and then malloc?
Yeah.
Okay.
Yeah, malloc is no different from any subroutine that we are calling.
So it'd just be like there was a subroutine that we already wrote. That
Exactly.
We wrote ourselves in assembly.
Yep. Yep. The assembler really doesn't care. You know, when you say call malloc, you know, literally CALL space malloc, the assembler would basically say, okay, call is the instruction, the destination is the label malloc. Now the assembler would say, well, it's not in the same file, but it's okay because the linker will probably figure out, you know, where malloc is. We are not going to use LD for linking. We're using GCC for linking, and GCC automatically will link with the standard library of C, where, you know, malloc is actually located. So it should all work out.
Okay.
Okay. All right. So with this out of the way, yep, go ahead.
I'm just curious, does it have anything to do with new? I know malloc is something like new.
It's kind of like new. New is malloc in C++, and malloc is the original C concept for allocating from the heap. But since this is a regular C file, I cannot use the new operator because the new operator applies only to C++ and not in C. Yep. Okay, good question. Any other questions related to this? I just kind of want to add on to what I just said a little bit earlier. Because the new is an operator in C++, you can actually override the new operator. So depending on the class, a class can override the new operator to do something other than allocating from the heap, which is kind of interesting and useful sometimes. All right. So with this out of the way, let's go ahead and look at the process of getting started. So I'm not going to give you any actual code, but I will give you enough stuff to get started. Okay. So let's say you're ready to convert LSTR write into assembly code. Okay. So what you do is two things first. Okay. The first thing you need to do is to go into the make file and just understand a little bit of what it does. Okay. C source defines all the C source files. So once you want to change and not use the C version of LSTR write, you have to comment it out so that the make file does not think, oh, okay, LSTR write is coming from a .c file. So you have to comment it out first. And then the second thing you have to do is to add the source file in assembly into ASRC, which is assembly source file. So you have to add it here. Okay. I would use the same name and just with a different extension, okay? And make sure your extension is uppercase S because lowercase s is not going to work. It has to be uppercase. Okay, these three entries are also really useful. This is the source code to generate the include file used in assembly. So you have to write that file. I'll give you an idea of how to write it today. I think we did some of that the other day already, but today I'll give you an idea to do that too. This is the executable name of the include file generator. This is the name of the include file, for assembly code. All right. Okay. So now that I have made the necessary changes to the make file, let's get out of the make file. And then you will change the name of the .c file so that it doesn't end with a .c extension, because otherwise make will still be using the .c file because it has a preference to use .c file whenever one is found. So we have to move or change the name of LSTR write.c to something that has a different extension. That's all we need, is to change it to c.bak. That's my personal favorite. Because now you still have the source file, it's just the extension is not going to be picked up by make. right, and then we can now do the lstr write.s. Okay, several things I can just tell you right away. What you need is you will need to include lstr.inc, which is the include file. It's not generated yet. Okay, so we'll deal with this later. You also want to include lstr.def.h. Even though this is just a header file, it is still okay because it only includes a pound define of a macro. So it will still work in assembly. It's no big deal. You also want to do a .global, which is exporting the label lstr write, because otherwise the linker will not be able to find lstr write as a label. And then you define the label as the entry point of the subroutine, and do whatever you need in between. Okay, so I'm not going to give you the actual body of the subroutine, but what you need to do is to fill in, between line 4 and line 5 with the actual body of the subroutine. Okay, so this basically sets up a skeleton for lstr write. Okay, and if you do a make, it's not going to work at this point. Okay, because we let's make it clean first. So after you make all the changes, do a make clean. It doesn't like that either. Okay, so change the instruction, do a make clean before you make changes to the make file. But if you have already done this, you can always just remove the .d files and the .o files, and then you can make again. And it will complain because we don't have an lstr.inc file yet. So the way to do this is to do a touch lstr.inc. That will basically generate an empty file so that make feels that it is okay to do so. So are there any questions? The touch command is actually very important, because if you don't give it an empty lstr.inc file to begin with, it's not going to be able to figure out the dependency itself. So it's kind of cyclic in terms of the reasoning. So that's why you have to do a touch first, just so that it knows it can go through the process to figure out the dependency of the source files on header files. But once we have done that, now it knows the rest. Okay. I have included a lstr include generator source file, which doesn't do anything. So this is one thing that you have to do as well, is to figure out what to put in here. This file has to do several things, so I'm not just going to comment it here, but you have to do it in your version of the code. So you're going to need a lot of printf statements. Printf statements to print label definitions of displacements to individual members of a struct lstr node. Okay? And on top of that, you also need a label definition of the size of a struct lstr node. Okay, do you guys know how to do that? Generate a label definition of the size of a struct lstr node. Which operator in C can tell you the size of a structure? Size of? So you just need a printf statement, so that it says, in this case, I would use a label called lstr node underscore size, or size of, it's up to you, equals to, and then %d in the format string, and then after the format string, you supply size of struct lstr node. So that's how you can generate that entry. Because the purpose of this particular program is to generate the include file. And obviously, in order to understand what an lstr node is, this file definitely needs to include lstr.h, which is the C version of the include file, which includes the structure definition. Is that okay? So there will be some printf statements here that I'm not including, but when you go through, I think what we did on Tuesday actually has this part too. So I'll be okay with this part. Let me double check and make sure the recorder is still running. Occasionally it stops working because I hit the cable and it would disconnect the USB microphone, and then the recorder would go like, ah. Is that part okay? Okay, so now let me go back to what we worked on the other day, which I think is under the folder struct. And this one has a struct x include generation file, which has the same nature, and this is kind of what you need to do. Well, not kind of, almost exactly what you need to do with several changes. All right, so are we doing okay so far in terms of understanding how the different pieces plug in and work together? Okay, I can draw a picture. It's easier to draw a picture on the whiteboard in this case. Okay, so we have a include. Oh, this is not working. Drag erase. Oh, even worse. Okay, we have an include generation, something, .c file. This will, give us a executable. The executable is named the same way, include, generator, and that when you run this program, it will give you the something.inc file. That is going to be pound included in your .uppercase s file. The source file in assembly is going to pound include this file that is generated by the include file generator. The include file generator source file is going to have a pound include, in our case, lstr.h. So there is a dependency of this .c file on that header file. When I change that header file, or anything that this header file also pound includes, it will trigger the recompilation of this file, which generates a new executable. The new executable will regenerate the include file, and because your file, your source file, depends on the include file, it will also get reassembled. So the changes will all be propagated automatically using make. Am I doing okay so far? Okay, let me show you what I mean by that automatic propagation. So let's go back to the folder corresponding to your homework assignment, long string, and I think it has all the necessary stuff already. And what I'll do is I'm going to change how big a chunk is. The how big a chunk is, it's defined in lstr.def for definitions.h, and it really is just this item here. So if I just make one change here, instead of having a chunk size of 4, now we have a chunk size of 8. I save this file. If I make again, it will propagate all the changes to all the object files and also eventually to the executable. So let's do a make here and see how much it has to do. You can see that it knows to recompile the .c file because the .c file has a pound include of lstr.h, which in return pound includes lstr.def.h. It recompiles lstr read and write. Okay. It also recompiles. You can see right here, the include file generator is also recompiled because that also has a dependency on the macro definition. And because the executable is now regenerated, it will also regenerate the include file. So the include file, if you have an entry that is sensitive to the chunk size, will now be updated. Now that the inc file is regenerated or updated, it will trigger the recompiling of your code. Your lstr write.s will also be recompiled because it has a dependency on the include file. So you can kind of see how this tool chain is set up so that it minimizes what you have to do when you update something. And I can already tell you how I'm going to grade this one. So the way this particular homework assignment is going to be graded is I will test it for functionality. In other words, I'm looking for the output that is basically a repetition of the input twice. Okay, that's the functionality. But before I test it, I will make changes to 2 files to make sure that your code can handle the automatic update of everything. So the first file I'm going to change is the one that I just talked about, which is lstr.def.h. So I can come in here and arbitrarily change the chunk size to 16, 32, 15, some really oddball number. It should not matter at all, okay? That's the first thing I'm going to change. The second thing I will change is lstr.h itself, and I can say, just include some additional member at the beginning of the structure. It should not impact your code whatsoever. As long as I'm not removing any member that is already here, any additional members, interchange, like J, inserted between chunk and P next, or moving P next to become the first member, all of these changes, your code should not be sensitive to at all. Okay? Because if I do all of this stuff here and do a make, what's going to happen?
It's gonna get updated.
Yep, the rules will basically make sure that everything is recompiled whenever whatever component needs to be recompiled will be recompiled. So it is up to you to make use of the symbols defined by the include file generator. Okay, so that really is the most crucial part from your perspective. So don't hard code anything. Okay, do not hard code, chunk size to be 4 or 8 or anything like that. Just refer to the macro definition, because you can use the macro definition in your assembly code. Are there any questions to related to the homework assignment? I got a question. Should I start now, like today, or should I wait until next week, like maybe next Wednesday, to get started on this homework assignment?
Next Wednesday.
Next Wednesday, maybe next Thursday. Like 4 a.m.
Class,
Yeah, right before class. No, get started as early as possible. Okay, this is the kind of thing that you want to start early, just so that in case you have any questions, in case you run into something that you cannot solve, then you can bring it to the class on Tuesday. Okay, then we can talk about it. Okay, but definitely get started on this one as early as you possibly can. Any other questions? No other questions? Yep.
Not related to this though.
Go ahead.
The final, is that at the regular time or is that at a different time?
The final is on the syllabus, I think.
I didn't see it, so.
Sometimes I forget. Okay, let me check.
December 16th, 8 to 10.
Yeah, if it's in the syllabus, it will be in the first part, or the part that is section information.
Oh.
Okay, so it is on the 16th, and it is from 8 to 10 a.m.
Yeah,
Sorry.
and that corresponds with the exam,
This is the final exam. This is our final exam time.
the exam schedule.
Will that be here in this room?
Yep, it'll be here in this room, and it's going to be a paper exam. Okay, it's still open book and open notes. No electronics, but open book, open notes. So it's just like with the midterm. You can bring in anything that is either handwritten or printed prior to the test. If you have found textbooks that might be useful, bring those. If you find that some of the homework assignments might be helpful, bring the listing of the programs. Just about anything that is handwritten or printed is fine. Before the test, if you guys want to study together and come up with the same set of notes to bring to the exam, that's fine too. It's just that there will be no exchanging of material during the test. Yep.
Is the instructor like this the other final?
Sorry?
Would like the instructor like the last thing they did?
Yes. You will not be asked to write algorithms like what we are dealing with here, but I can give you a particular line and ask you, how to translate that into assembly, or I can give you a line in C code and I'll give you the code in assembly code and ask you to debug it, like, okay, find all the flaws with this chunk of code and fix it. Or I can give you a chunk of code in assembly and you have to reverse it back into the C notation. So all of those types of questions still apply. It's just that now we're dealing with structures. Okay. Any other questions? Well, if there are no other questions, let's go ahead and I'll give you some additional clues that might be helpful to your homework assignment. So we'll go back to struct here, and I think we did not have time to implement initx, so we'll do this today. So we'll go ahead and do a side-by-side display of initx dot uppercase s and initx dot c.
That's lowercase s.
Yep, thank you. So we'll do this part here, okay? Because it does seem like it is resembling something that you have to do. I mean, not everything, but something. Okay, so let's go ahead and figure out how to implement the C code on the right-hand side in assembly, which is on the left-hand side. Okay. I personally like to use the use of definitions in symbols. So what I usually do, you don't have to do the same thing, but I find it useful for myself, is EBP is 0 because this is all expressed in terms of displacement from where EBP as a register points to. It points to its own old value on the stack. The return address is right on top of that. And then the first parameter, which is the only one that we have here, is on top of the return address. So personally, I like to keep track of stuff like this. You don't have to do it this way because you can say, oh, that's just the same thing as 8. I'll just use the digit 8 throughout the program. That's fine. Okay, I just find this way to be more readable. The program is a lot more readable this way. Entry code and exit code, I will deal with those. Getting out of the way first. Push EBP is matched by pop EBP. And even today, even though I have written programs like this, many times, I still write it this way, just so that I know that whatever I start with has a matching end. Okay, so this is still the way I do things, even though I can probably write the program from start to finish without doing it this way. But I like doing it this way just because I can match the beginning construct with a matching end construct without having to worry about that later. Okay, so now in between, I don't have any local variables, so I don't have to do anything to adjust the stack pointer. But if I do have local variables, this would be a good time to subtract something from the stack pointer to allocate for the local variables. And I would have defined displacement or offsets as symbol names to access those items. Okay. Okay, so now we want to initialize member I. Okay, let me point to where I'm working at this point. So I'm working up with this statement here. I want to initialize member I of the structure pointed to by PTR to 0. That's what I want to do. What I do have access to right away is the parameter PTR. Okay, so the first thing I'm going to do is to say, well, since we do have access to the parameter, let's put it into a register and then see what we can do with that register. Okay, so after line 11 in the assembly code, EAX is now pointing to the beginning of a structure, right? It's pointing to the beginning of a struct X. Is that part okay? Because that's what the pointer is. The parameter is supposed to be a pointer to a struct X. So now that I move the parameter or copy the parameter into EAX, EAX points to the beginning of a struct X. Okay, and it's not the entire struct X that I want to initialize to 0. It is just the member I that I want to initialize to 0. So even though EAX is going to be pointing pretty close to what I want to change, it may not be exactly what I want in order to change it. So I need to figure out what is the displacement from the beginning of the struct X to member I of a struct X. At this point, I don't know. But you know what? I can now refer to x.inc, which is the include file. Oh, that's not the name of the include file. I cannot remember what I used for the name of the include file. But typically, the symbol that I would use is x underscore I, in this case, x being the name of the structure and I being the name of the member that I want to access. So the next thing I need to do is to move a 0 to x underscore I of EAX relative to EAX, because EAX is a pointer to the base of the structure. X underscore I is the displacement in number of bytes from the beginning of a structure to member I. So this particular base operand will specify the memory location of what I need to change to 0. So that will take care of the first line in the C code. Are we doing okay so far with this code? Next, we have to deal with the first byte of buffer being a 0. Okay, well, that's actually pretty easy because I have to move byte in this case because it's a character, and because the first byte of buffer has the same address as buffer itself. So that's why I don't need to do any really special calculations here. And the last one is ch. Well, it's going to be almost exactly the same thing because ch is a byte also. So I just have to change the displacement to ch, and assuming my include file generator is exporting these labels correctly, this will get a job done. Are we doing okay so far? It's all good? Okay. So with this out of the way, we're gonna, I want to fix this so that this actually works. So I think the reason why it's not working is because I don't have the source file included here. So I'm gonna include that here. And oh, this is what I'm missing. Include generator executable depends on include generator source. It does not have any assembly code, so that's what I'm missing. And when we clean up, I'm not going to worry about that. So do a make. It doesn't know what I'm trying to make here. Yeah. So I will have to uncomment that one and comment this one out, and then change init x dot uppercase s c to init x dot c dot bak. Do another make. Okay, now it figures out the dependency, but it doesn't know what to do with main. It cannot find the dependency of main to the source files. The first target, which is on line 15, the executable, is the default target. So if I say make without making anything, that's the default thing that it's supposed to make. But it's not doing that. Let's check all the .d files. So we have a .d for struct itself. We have a .d for struct include generator, and we have a .d for init x.d. So all the .d files are present. And this one does have the correct dependency, but it's not making main. We can do that. So remove all the dependency on the object file. The include file needs to be maintained. So I'm going to say, there we go. It did all the compiling, but it's not doing the linking. The first 3 compiling, that's for figuring out the dependency and output to the .d file. The other type, these 2 are just compiling from C to .o, so it's creating the object files, and same with this one. But it cannot figure out how to make the actual executable. So whatever problem is, it's going to be with line 15. It's having a problem associating the .o files, and understand that's how it's going to use. That's what it needs to use to make the executable. I don't think that really is going to solve the problem. Oh, it does. Interesting. So anyway, that solve the problem. Okay, now that we have everything fixed here, we can actually go ahead and debug the program using GDB. And main is still the same in C. So what we'll do is we'll put a breakpoint on line 6 and another breakpoint on line 7. So we get to line 6 and we say, okay, show me what is var1 before it is initialized. And not surprisingly, we get a whole bunch of gibberish. In fact, it's consistently the same gibberish as last time. We continue execution. Well, actually, we can single step now because the assembly code is my code. We can actually go into the assembly code, single step through the assembly code like this, get back to the main subroutine, and print var1 again. And you can see, everything is now properly initialized. So yes, you can debug programs that are partially written in C, partially written in assembly, and as long as you assemble and compile using the -G option, the debug information will be in the object files, and you can basically cross over from C to assembly code and back to C whenever you need to. All right. Any questions about this? Questions? All right. So we are running out of time today, and this is your homework assignment. I will get started as early as possible. Hopefully today I'll be at the lab in case you guys need help with at least setting it up so that Make can automate everything. Okay. All right. So I'll see you guys. If you're not going to the lab, have a nice weekend, and I'll see you on next Tuesday.